Welcome to SS2 Chemistry, Term 2, Week 2. The quantum mechanical model of the atom describes electrons not as particles in fixed orbits but as waves occupying regions of space called orbitals. Quantum numbers specify the energy, shape, orientation, and spin of each electron. By the end of this lesson, you will define the four quantum numbers, describe the shapes of S, P, and the orbitals, write electronic configurations using both shell notation and subshell notation, and apply Aufbau, Pauli exclusion, and Hund's rule. Let us begin. Quantum numbers describe the quantum state of an electron in an atom. Four quantum numbers are needed to uniquely identify each electron. Principal quantum number then describes the main energy level, shell, n equals 1, 2, 3, 4. Positive integers, as n increases, the electron is farther from the nucleus and has higher energy. For the first 20 elements, n goes up to 4. Azimuthal, angular momentum, quantum number, L describes the subshell and the shape of the orbital. L ranges from 0 to n. 1, L equals 0 is the S subshell, spherical. L equals 1 is the P subshell, dumbbell-shaped. 3 orientations, L equals 2 is the D subshell, complex shapes. 5 orientations, L equals 3 is the F subshell, complex. 7 orientations. Magnetic quantum number, M_L describes the orientation of the orbital in space. M_L ranges from L to plus L, including 0. For L equals 1, P subshell M_L equals -1, 0, plus 1, 3 P orbitals, Px, Py, Pz. For L equals 2, with D subshell M_L equals -2, -1, 0, plus 1, plus 2, 5 D orbitals. Spin quantum number, M_L describes the spin of the electron, only two values, plus 1/2, spin up, shown as arrow pointing up, or -1/2, spin down, shown as arrow pointing down. No two electrons in the same atom can have the same set of all four quantum numbers. This is the Pauli exclusion principle. Each subshell contains a specific number of orbitals. S subshell, L equals 0,1 orbital, is spherical, centered on nucleus, holds maximum 2 electrons. P subshell, L equals 1,3 orbitals, Px, Py, Pz, dumbbell-shaped along x, y, and z axis, holds maximum 6 electrons. D subshell, L equals 2,5 orbitals, holds maximum 10 electrons. F subshell, L equals 3,7 orbitals, holds maximum 14 electrons. Summary by shell, shell 1, n equals 1 only one subshell, 1 orbital, 2 electrons. Shell 2, n equals 2 twos, 2 electrons, plus 2p, 6 electrons, equals 8 electrons maximum. Shell 3, n equals 3 threes, 2, plus 3p, 6, plus 3d, 10, equals 18 electrons maximum. Shell 4, n equals 4 fours, 2, plus 4p, 6, plus 4d, 10, plus 4f, 14, equals 32 electrons maximum. Subshell capacity formula, each subshell holds 2L plus 1 electrons. For S, 2, 1 equals 2, for P, 2, 3 equals 6, for D, 2, 5 equals 10, for F, 2, 7 equals 14. 3 rules govern how electrons fill orbitals. Rule 1, Aufbau principle, German, building up. Electrons fill orbitals in order of increasing energy. The order of filling, Aufbau order, is 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p. Note that 4s fills before 3d, a crucial point often tested in WAEC. This can be remembered using diagonal arrows on the orbital energy diagram. Rule 2, Pauli exclusion principle. Each orbital can hold a maximum of 2 electrons, and they must have opposite spins, one spin up, one spin down. Rule 3, Hund's rule of maximum multiplicity. When electrons are added to orbitals of the same energy, they generate orbitals, e.g., the 3 2p orbitals. Electrons occupy each orbital singly before any orbital is doubly occupied, all single electrons in degenerate orbitals have the same spin. This minimizes electron-electron repulsion. Example: carbon Z equals 61s2, 2s2, 2p2. The two 2p electrons each occupy a separate p orbital with parallel spin, not both in one 2p orbital. Using Aufbau order, write the electron configuration of these elements. Sodium No. Z equals 111s2, 2s2, 2p6, 3s1. Abbreviated 3s1 using the noble gas connotation represents 1s2, 2s2, 2p6. Chlorine Cl Z equals 17 1s2, 2s2, 2p6, 3s2, 3p5 or 3s2, 3p5. Calcium Ca Z equals 21s2, 2s2, 2p6, 3s2, 3p6, 4s2 or 4s2. Iron Fe Z equals 26 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6 or 4s2, 3d6. Note: force fills before 3d, but when writing the full configuration, we often write 3d before force to group subshells by principal quantum number. Ionic electron configurations: when atoms form ions, electrons are added for anions or removed for cations. For cations, electrons are removed from the highest energy subshell first, and for d-block elements, force electrons are removed before 3d. Example: Fe2+, an ion loses 2 electrons from force 3d6. Fe3+, 3d5. Chloride ion Cl- gains 1 electron to 3p6, 3s2, 3p6 equals isoelectronic with Ar 18 electrons. Sodium ion No+, loses 1 electron from 3s equals isoelectronic with Na. Key points: for quantum numbers, n, principal/shell, l, azimuthal/subshell/shape, m_l, magnetic/orientation, m_s, spin +½ or -½ Pauli exclusion principle: no 2 electrons can share all 4 quantum numbers, maximum 2 electrons per orbital. Subshell capacity: S equals 2, P equals 6, D equals 10, F equals 14. Aufbau order: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. Note: force fills before 3d. Horn's rule: fill each degenerate orbital singly before pairing. For ions, cations lose electrons from highest energy first, force before 3d. WAEC chemistry regularly tests electronic configuration writing, identification of errors in given configurations, and the reason why certain configurations represent ground state versus excited state atoms.